Welcome back to multivariate calculus. In this video, we're going to be looking at the method of Lagrange multipliers. Previously, we started talking about the extrema of a function of several variables. And we developed a nice tool that was pretty analogous to the first derivative test and the second derivative test for finding relative extrema of one variable, and we use that to find relative extrema of functions of several variables as well. But if you think back to how you used extrema of a function as a problem-solving tool when you were dealing with functions of a single variable in Calc 1, the big idea there was we weren't looking at relative extrema, we were looking at absolute extrema. And when you think about a function of a single variable, and you think about absolute extrema, remember that if you are on a bound region from A to B like that, there will be extrema, there will be a maximum, there will be a minimum. It might occur at a point of relative extrema, the kind of thing that we were looking at in the previous lesson. But that's not the only option. It could also occur at one of the endpoints of the interval. Now, when we were dealing with a function of one variable, the endpoints of the region that we care about are very straightforward. They are point A and point B. That's it. If you're thinking about a surface and a function of several variables, that's when things start to get a little bit messy. Because the region that we care about is now an area in two-dimensional space. And if you're trying to figure out what the function is doing above that area, well, sure, you can look for relative extrema in that area, but you also have to test what's happening on the boundary. And if you look at this boundary, there are infinitely many points. That's a problem. One way of dealing with that is to figure out a vector valued function for x and y that traces out the boundary of the region that you care about down here on the xy plane, create a vector valued function that traces out that parameterized path, project it up to compose with the function that is our surface, and then you have f of t, a function that is tracing along the boundary. You can find the maximum and minimum of that using the tools that you learned in Calc 1. And then your extreme values are either the extreme values of the boundary or something that happened at an interior point of the region where you had relative extrema. That absolutely works. There's nothing wrong with that. But if that sounds unpleasant to you, I'm in the same boat. And so that's where the method of Lagrange multipliers comes in. Lagrange multipliers gives us a tool for thinking about a system where we are trying to optimize something given a particular constraint, where we don't have to go and think back to all of this. So let me get my head out of the way and let's look at a particular example. A classic example for optimization is finding an area. All right, so for example, I want to find the area of the largest rectangle, which can be inscribed in the ellipse x squared over 25 plus y squared over 16 is equal to 1. Before I get into any actual problem solving with that, let me jump over to Desmos, and I've used Desmos, not GeoGebra, to graph this one, because specifically I wanted some sliders. And so here's the picture that I'm talking about. We have, if I get out of the way, we have an ellipse. X squared over 25 plus y squared over 16 equals 1. It's a fairly simple ellipse to work with. And I have found 4 corners of a rectangle on the ellipse. I'm going to assume, for the sake of simplicity, that my rectangle is going to be um, oriented in a normal way with the x, y axes. So I'm not going to worry about what happens when I twist the rectangle around. It's very difficult to draw a rectangle in those circumstances. So we'll assume that the rectangle has sides that are parallel to the major and minor axis of the ellipse. But if I move those points, and my slider here, A, is the x-coordinate of the point in the first quadrant, and then I'm just taking the negatives to get the mirrors of that in the second, third, and fourth quadrant. But I can slide that x-coordinate around, and I can create rectangles of different areas. Calculating the area of a rectangle is fairly straightforward. You simply multiply the length times the width. Although you have to be a little bit careful thinking about the length and the width here. Let me switch back over to my notes page so that I can draw this picture out in much less detail, but give us some discussion points here. The key to pay attention to on this, and again, I'm not trying to draw this in any significant detail, the coordinates of this point are x, y. They are an x and y coordinate that satisfy that equation. The coordinates over here are minus x, y. I have x minus y and minus x minus y. Because when we're squaring something, whether it's positive or negative to start, it ends up positive. So we know we are not going to get anything extra or lose anything in using this. But with those coordinates, the length and width of this rectangle are not just x and y. To go from minus x to x, that's a distance of 2x. And to go from minus y to y, that's a distance of 2y. So the area of this rectangle is, writing things faster than I'm talking, two x times 2y, which is 4 times x times y. All right. And so I have now reduced this problem to something entirely mathematical. We have a function f of x and y is equal to 4xy, and we want to find the extrema of this function. But again, we're not looking for the relative extreme values. We are looking for the absolute maximum and the absolute minimum that satisfy the constraint x squared over 25 plus y squared over 16 is equal to 1. I'm going to go ahead and name this thing as, I called it g of x. It should be, of course, a function of two variables. G of x and y is equal to 1. Mathematically, this is something that we will always be able to do with our optimization problems. We can take our situation and turn it into an object function, f of x and y is equal to 4xy, and translate the situation into find the maximum or find the minimum value of this object function, or find the points where the maximum and minimum occur, depending on the particulars of the problem in question. But then it's always subject to a constraint where you have some other function we'll call g and force that to be equal to 1. All right, so there is our setup. Now that we know the setup, we can ignore the fact that this came out of a particular situation, and we can dig in and just solve the thing. All right, we have a function of several variables, so I guess a natural thing to do is going to be to try to graph this function z equals 4xy, and think about what that graph is doing. If you want to fire up GeoGebra or something like that, go ahead. It's certainly not a wrong thing to do, but I'm not going to because it doesn't really gain us anything to see the graph. Instead, I want to think a little bit about how we can analyze the graph using other tools. Specifically, we can think about this graph by plotting out its level curves. 4xy equals k, for k equals 0, 1, 2, 3, and so on. All right, well, 4xy equals k is not something I know how to graph, but if I just rearrange this ever so slightly, y equals k over 4x. I know what all of these curves look like. Right? I know what the graph of a reciprocal function looks like, and I know that multiplying that reciprocal function by a constant is just going to change the amplitude. Right. Once again, I'm not going to try to graph this by hand. I'm going to jump over to Desmos and let it do the work for me. You can see that I have an equation written here, 4xy equals k, and I have a nice slider for k. Currently, that bar in green or yellow or whatever it is right across y equals 0 is the graph. But if I slide this around, we can get set it to 4. There's y equals 1 over x, the standard reciprocal function that you tend to think about. And as I move this around, you can see that it slowly starts to spread out before eventually getting nearly off screen. All right, slide it back down. We'll get this thing to come closer together for us. All right. Now I can ask an interesting question. What does this curve represent in our application? What are we looking at here? And can we ascribe any meaning to it? Well, of course we can, otherwise I wouldn't ask the question. But remember that this function, z equals 4xy, or f of x equals 4xy, is designed to calculate the area of the particular rectangle, the thing that's shaded in green. So if I move my slider on A so that those points come as close as I can get them, just eyeballing things, to the intersection point of that hyperbola, the reciprocal graph, then that means that for a point going through that coordinate, remember, that means that x and y satisfy the ellipse, so they satisfy the constraint, they satisfy the conditions of the rectangle, and they also satisfy the equation down here that is calculating the area. So the area of that rectangle is 20. And if I slide around so that I get way over here to, I guess that's as close as I can get, the constraint or the point on that side, again, we're as close as we can get. So the area here is somewhere in the ballpark of 20. And given that x value, you can plug it in, calculate the y value, you can calculate the area, you can see that that works for yourself. I encourage you to do that, but I'm not going to take the time to for the sake of this video. So what are we looking at here? The level curves of our constraint are telling us where the intersection points happen, where we can draw the corners of our rectangle so that we get a specific area. And if our goal is to find the maximum area, another way of phrasing that is we're looking for the value of our constraint k here that gives us the largest value of k where the hyperbola, the graph of the reciprocal function, still intersects the ellipse, the graph of the constraint function. If I get my head back out of the way, I can play around with that slider. All right, let's slide this value of k around until we get it to look as close as possible to having only one intersection point. And it looks like there we're past, so it's going to be closer to there. Although in practice, probably a decimal somewhere in between. Then we go to our slider for A and we slide it around until we get as close as possible to that intersection point. Again, if we had more precision, we could get something better, but it looks like it's going to be pretty close to that, pretty close to 3.5. Right? Based on our graphical analysis, we can say that this is going to be the maximum area that we can get. But graphical analysis has the problem of always being an approximation. So let's see if we can find a more powerful tool for doing the same thing without having to rely on approximate values. We are looking for the level curves of a surface that satisfy a particular equation. We're looking for the place where the level curve comes as close as possible to not being able to satisfy anymore. So let's switch back over to the lecture notes and see what we can do with that. All right. So that transition point where we go from the intersection having multiple occurrences to having exactly one to no longer touching at all, that is going to be two curves that are tangent to each other. And two curves tangent to each other is not really something that we have thought about previously. So we need to think about a different way of setting that up. For two curves to be tangent to each other, well, one way to think about that is that they have to have the same tangent line. And we know that they will share that one point in common. That's something that we can guarantee from the setup that has gotten us this far. All right. So another way of thinking about that is that we need to have the tangent lines in the same direction. And we have a function of several variables that we need to figure out how to write the direction of the tangent line in. So we know that we can find the direction of a parametric curve by differentiating. It probably makes sense that we can find the direction of a level curve here by differentiating as well. Right, so I'm going to differentiate f of x and y. And I am going to differentiate g of x and y. By taking the gradient, I know that I am looking in the x direction, the x components together, the y direction, the y components together, and it's just a matter of bringing everything together. Now, the problem with finding directions as vectors is that I don't want to just say that these are equal to each other, although I would love it if they were, because we know that you can take a vector and multiply it by some constant, and it's pointing in the same direction. The most elegant approach would be to find the unit vector in each of these directions, but that is really mathematically messy. So we instead just look at, let's multiply one of these by some constant. We'll call that constant lambda, and it is the Lagrange multiplier, the name of the method here. It is called the Lagrange multiplier. In practice, it is some arbitrary constant, and that's all you really need to know. Right? But there is a tool that we can use. So thinking through the problem logically, we know that this process should work. So let's go and take a look again at our example. We had that f of x and y is 4xy. If we take the gradient of f of x and y, we will get the vector valued function whose x component is the derivative with respect to x. and whose y component is the derivative with respect to y. Then we'll take our constraint. Our constraint was that g of x and y was equal to 1, but it's just the constraint function g of x and y that we care about. And that was given as x squared over 25 plus y squared over 16. And again, our constraint was that g of x and y is equal to 1, but actually, let's go ahead and write that one down. So we know that the gradient of this will give us a vector valued function. X component is derivative with respect to x. That's going to be 2 over 25 times x. Y component will be the derivative with respect to y. That's going to be 2 over 16, which I can reduce and call 1 over 8 times y. So we know that delta f is some lambda times delta g, and we know that g of x and y is equal to 1. With just those constraints, we can write out each of those equations. For two vectors to be equal to each other, component by component, they have to be equal to each other. So the x component gives us that 4y is equal to our multiplier lambda times 2 over 25x. Our y components give us that 4x is equal to our multiplier lambda times the y component 1/8 y. And then, of course, g of x and y is equal to 1 gives us that x squared over 25 plus y squared over 16 is equal to 1. A system of 3 equations with 3 unknowns. 2 unknowns that we care about, x and y, plus an unknown that we don't actually care about. It does not matter what the value of lambda is in finding our solution. Lambda is incredibly important because it lets us set up this system, but we never care to actually solve for it. Or we never care to actually find the value of it. In fact, because of that, my usual approach from this point is to solve each of these equations that have a lambda for lambda, and then set them equal to each other and go from there. Right. I'm running low on space, so let me copy this system to somewhere that I can actually work with it. And let's do exactly that. Let's rearrange this first equation. Multiply by 25 over 2, divide by x. Looks like we're going to end up with 50y over x is equal to lambda. Multiply this equation by 8, divide by y. It looks like we're going to get that 32x over y is equal to lambda. And then bring these equations together. We get that 50y over x is equal to 32x over y. And I can rearrange that a little bit. Two fractions equal to each other, cross product test, 50y squared is equal to 32x squared. And then we just choose, do we want to solve for x, do we want to solve for y? It doesn't really matter. I'm going to look for, actually it would be best if I could get x squared over 25 or if I could get y squared over 16. And those are actually pretty easy to come up with. If I divide both sides of this equation by both 50, actually, by both 25 and by 32. Notice here, divide by 2 first, actually. 25y squared is equal to 16x squared. Y squared over 16 is equal to x squared over 25. The fact that both of those are exactly what shows up in that equation is kind of a coincidence, but also very useful. So just plug one in for the other. I'm going to take my x squared over 25. I'm going to replace it with y squared over 16. Again, just taking this and substituting it in over there. Simplifying, y squared over 16 plus y squared over 16 is 2y squared over 16, or y squared over 8. And I get that y is the plus or minus square root of 8. Take that, plug it back in over here. If y squared is 8, that means that I have 8 over 16 is equal to x squared over 25, which means that 1/2 is equal to x squared over 25, which means that x itself is 25 over 2. And taking the square root, I get 5 over the square root of 2 is equal to x. I can simplify, I can rationalize. I probably will do that. So that would be that x is 5/2 the square root of 2, and y is 2 times the square root of 2. And again, we take the positive and negative of each of those, and we get the 4 endpoints of our rectangle. All right, and that's the method of Lagrange multipliers. Going back to our original problem, if we so desire, the maximum area is formed by a rectangle with corners at 5/2 root 2, 2 root 2, and the negatives and positive combinations that are possible. And we can calculate the area, which is 4 times the x component times the y component. All right, root 2 times root 2 is 2. So we've got 4 times 5/2 times 2 times another 2, which is 4 times 5 times 2, which is 40. In fact, we got that as an exact value in the problem that we were looking at, trying to solve this graphically, which doesn't usually happen, but we had some nice numbers to deal with for this particular example. Here is a similar problem for you to try. I'd like you to use the method of Lagrange multipliers to optimize the function f of x and y is equal to x squared minus y squared, subject to the constraint that 2y is equal to x squared. All right. Compared to the one that we did, this one doesn't involve any processing the application and coming up with the equations on your own. I'm giving you an optimization function, f of x and y equals x squared minus y squared. I'm giving you a constraint, 2y equals x squared. Notice that that constraint is not exactly in the form that we usually see. So you have to do a little bit of work to rewrite the constraint into the form that we were talking about when we went through the earlier example. But take a few minutes, see if you can set this up, see if you can solve the problem, and I'll see you in the next video.